Everyone, today we're going to look at the potential or voltages found around continuous charge distributions, which means that there's charge around certain objects like a charged ring or a charged disk, charged spheres, charged lines. So all the things we found electric fields for in the past, we now want to figure out the voltage as we approach these objects or move away from them. Are we increasing our voltage or decreasing our voltage? If you look at this location, we are a z distance from the center of the ring. A is the radius of our ring, and technically from point P we're at that distance r away. So if I want to find the voltage for this charge distribution, we can treat each piece of the ring as a simple point charge. And when we do that, we can say that dV is equal to k dq over r, where we have to add up all the little pieces around the ring. Well, the nice thing about the ring is that whatever distance I pick, I'm still an r distance from that charge. So when I go to integrate and add up all the potentials from all the charges around the ring, what I can pull out are my constants, which is k and r, which leaves behind a dq. And the dq will be measured from 0 to q, all of the charge in the ring. So dq is a very easy integral. dq just gives me q, so I get k q over r. And sometimes they want you to write the voltage in terms of constants, not just your r position from the ring. So you can see that the constants there were the radius of the ring and the distance. So r would be the square root of a squared z squared. So I put that in there, and that would be my potential, my voltage from the ring. It would depend on the radius of the ring and my distance from the ring. Again, if we are very, very far away, so if z is much, much, much bigger than a, then a really doesn't matter in my formula, and I just have the square root of z squared, which comes out as just z, so my voltage is kq over z, meaning my voltage is just that of a point charge. If z equals 0, then what we talk about is z not mattering, our distance from the ring, and we are now in the center of the ring. And the square root of a squared is just a. So this goes to kq over a. And a, being a lot smaller of a distance than an r distance away, gives us our highest potential, our highest voltage when we're right here at the center. Remember, like we talked about in class, there is no electric field at the center of the ring. The ring is repelling a positive charge in all directions. However, there is a voltage. So it takes energy to take that charge from infinity and walk it all the way to this location. I have to fight a field the entire time to get it there. But once I get it there, it doesn't feel any push. So it just kind of sits in the middle of the ring and is at a high voltage or a high potential, but it doesn't have to move anywhere because there's no force on it. If it moves left or right out of the ring, then yes, it would accelerate away and decrease its potential energy. But what about the disk? Well, remember, the disk of charge is just many, many rings. So we're going to use our ring idea again, but this time we want to see that there is two things changing as we go from small rings in the center to the full disk. Okay, so what I can pull out now that is constant is really just the k. The charge is changing because I'm dealing with all the charge on different rings, and r is changing because I'm dealing with a small ring versus the next size ring versus the next size ring. So I can't pull out anything but my k value, which leaves behind a 1 over 4 pi epsilon 0. dq would be the charge on the surface area of a disk. So remember, charge per area is sigma. So dq would be my sigma dA. So I'd have to multiply by the derivative of area of a disk. Remembering that regular area is just pi a squared for each of the rings as I move from the center out. So dA would be 2 pi a dA. So I'll put that in for dA and throw that over here for my voltage equation. So we get a sigma 2 ADA on top, and remember the r distance is a squared z squared from our picture, we can eliminate some things here and pull out some constants, like I can eliminate the pi, and I can move the constant out front, leaves me a 2AdA over the square root of a squared z squared. This is where we pulled out u substitution. We'll make u z squared plus a squared. So u is going to replace everything in that square root down there, and that means that du ends up being 2a dA. 2AdA can be replaced out of my equation over here, like 2a and dA. Means I can knock out the pi, and I don't need that. And that leaves me a 1 over 4 epsilon 0 integrating du over the square root of u. So integrating u to the negative 1/2 power gives us, so there we go, we're going to evaluate that between 0 and r. So what that means is we've got a 2 that's going to come out front here. So my voltage is going to end up being sigma times 2 over 4 epsilon 0, and we're going to multiply by z squared plus r squared square root minus z squared plus 0 squared, which 0 squared will just be 0. So that is the voltage away from the plane. I can simplify a little bit more and make that 2 and 4 disappear. And if you look, this is the voltage outside of the surface of the disk of charge. So the way that they've written in the book here is that you could assume that if you're really close to the disk, you could see the disk as one flat plane. So you could have the voltage at the surface, and you can have that minus 2k pi sigma times the distance we are from the disk. The further we get from the disk, the weaker the voltage is going to get, because again, when fighting a disk, it takes work to take a charge from infinity and bring it close to the disk. So you're fighting the field from the disk of charge, and it's going to try and resist that change from infinity towards that high plane. If you want proof on where this comes from, the proof is in the textbook, or they at least refer to where you could find the proof of solving voltage to write it out like this. But let's look at spherical shells. For spherical shells of charge, we looked at electric fields inside and outside, and we used Gauss's law to find those electric fields. To find voltages, we can use those ideas we got from Gauss to look at how much field I'm fighting and where the field actually is. Our shell of charge, and we want to find the voltage inside and outside the sphere. So the first thing, let's go outside. The outside usually was easier because we took Gaussian spheres and we surrounded the outside with a Gaussian sphere, and we said, all right, is there electric field? So going back to Gauss, E dot dA is the electric flux, and there's electric flux if we enclose charge. Well, there is positive charge enclosed, so check on that. So that means that we can pull out the electric field since it's uniform at our distance of r to the Gaussian surface. dA becomes the surface area of our Gaussian sphere, which is 4 pi r squared. The charge enclosed is all of q, and epsilon 0 is our constant for permittivity of free space. Solving for the electric field outside, we get q over 4 pi epsilon 0, which remember that is just k over r squared. So it's following point charge, which we knew from way back when. But now let's apply that to voltages. So our definition of voltage is the electric field dotted with the displacement, and we know the electric field now is kq over r squared dr. So that means if I want to integrate and find my potential as I go from infinitely far away to the radius of the shell, so those will be my two limits, I pull out the constants, which will be k and the charge, and I'm left with a 1 over r squared dr. When you integrate 1 over r squared, you get negative 1 over r, so the voltage outside becomes kq over r. We've done that a couple times, so I didn't think I needed to go through all the derivation with you again. Remember, we can see the electric field as a point charge outside the shell, and we can also see now the electric potential, or the voltage, treats it as a point charge. Far away, our voltage, if we're at the radius, starts off at 0 and increases by a 1 over r relationship. question is, what happens on the inside? Okay, so when we look on the inside, we're going to put a Gaussian surface right in here. And what we can say is that, all right, let's go with Gauss and say E dot dA equals the charge enclosed over epsilon 0. But the nice thing is there is 0 enclosed charge. The Gaussian surface closes up nothing, which means that the electric field inside the shell is nothing. We said we could put a test charge in there and it wouldn't feel a force whatsoever. So that should be easy. That means that our voltage graph, it would increase as we get to the radius of the shell, and then it should drop off to 0. I mean, that's what we saw when we looked at electric fields. Why wouldn't voltage be any different? But here's where you got to think about this a little differently. Since there is no electric field, that means I don't have to fight anything to bring a charge once I'm inside the shell. And that's the key point. I don't have to fight once I'm inside the shell. But when I was outside the shell, there definitely was electric field, and the electric field was trying to resist me, and so you fought the field the entire way into the shell. But once you're inside the shell, you remain at the voltage of the surface. You kind of hit a plateau, and your voltage is nice and constant on the inside. Just because you don't have an electric field doesn't mean you don't have a voltage. So we get inside, we fought, and it's like raising a mass up a really, really high hill. And when you reach the peak, there's a nice level plateau. So you don't have to do any more work. You can just stay up there at that high potential. You don't need to fight anything anymore. The last one we want to focus on is the infinite line of charge. With the infinite line of charge, we have done many Gauss's laws to show that the electric field from a line of charge is equal to 2k lambda all divided by r. R being the distance from the line. So there is a different electric field strength here at our first point versus our final point over here. The electric field does get weaker from an infinite line of charge. So knowing that that is the electric field strength for infinite lines, let's use that to calculate the potential difference when I move from our reference point all the way to point P. Alright, so first thing I can say is that, alright, I know moving a positive charge from the reference point to point P is going to decrease my voltage. How do I know that? I'm moving with the electric field. So if I move with the field, I decrease my energy. So if I want to write this out, I know that dV is equal to negative E dot dr. And this time I know my electric field for a steady field, or my electric field for line of charge, and I'll be left with a 1 over r dr from my reference point all the way to point P. So let's just integrate 1 over r. That should be easy. That'd be r to the negative first, so I'm going to add 1 to the power and divide by the new power. So that makes our new power 0 and divide by 0, which means that doesn't work. But remember, a 1 over r integration is a special integral, one of those special ones that you do need to know for AP. 1 over r integral is actually the natural log of r. And we'll take the natural log of our two reference points, point P and where we started. So if I put in my two bounds, put in point P and put in my reference point, I would have to subtract natural logs. And there's an easier way to write the subtraction of natural logs. You can take the division of the natural logs. So the voltage away from a infinite line of charge is negative 2k lambda multiplied by the natural log of our reference point, or RP, over our reference point where we started. We're going to decrease voltage as we move further from the infinite line of charge. So there's a bunch of different charge distributions. We use the electric fields that we know using Gauss's law to help us calculate our change in potential when we move closer or further from these charge sources.